Hello, everyone. It's just been a wonderful experience here, Walter. Thank you so much. And it's very good to meet everyone, and I learned very much from the formal talks and the informal talks. I'm going to tell you two things, TABI-PB 2.0 solver, and then more recent, very recent, an integral equation method, so far just for the 1D steady state PNP equations. And I have to thank many collaborators. We'll see their photograph at the end. Former students and postdocs, current student and postdocs. And let's see, why doesn't it? Okay. So I don't have to belabor the point. The first part of the talk is about the Poisson-Boltzmann model of a solvated biomolecule. And so the Poisson equation in the interior representing the solute, and then the Poisson-Boltzmann equation in the exterior. This is the linearized. By the way you solve nonlinear equations is you iterate linear equations. So we haven't done a nonlinear PB solver, but I think this method can be made to work for the iterations one would need to do the nonlinear PB as well. But this talk will be about the linearized PB equation. And so the approach that I take, and I'm an applied mathematician, numerical analyst. I began working in fluid dynamics. And the methods I used there involved converting the PDEs, the differential equations, into integral equations. And then when I drift over into this area, I want to do the same thing. So we're going to convert the differential equations that we see here into integral form, and then solve them with a boundary element method. So you've seen this a few times already. This is the Juffer formulation of the linearized PB equations, the model that we just saw. The two Green's functions over here. These are the integral equations. So what's highlighted in blue are the unknowns, the surface potential, the normal derivative of the surface potential. And this is a well-conditioned, and the kernels are defined here in terms of the Green's functions. So we have this one here is a single layer. These are double layer. These two are double layer potentials. This one over here, with two derivatives, it would be hypersingular. But the good point of this formulation is that it involves this subtraction, and so that weakens the singularity, turns it into a principal value integral, which can be handled. And so this is a well-conditioned form. It's the integral form of the PB equations. The source terms over here come from the atoms and then derivatives. So the approach is to use a boundary element method to solve these equations for the phi and the phi dn. And so we triangulate the interface. We take it to be the molecular surface, the Connolly surface. We discretize the integrals that you see here. That gives a linear system. Now these are now associated with the triangulation, linear system solved by GMRes. And what we're going to do is compute the matrix vector product at each iteration by a fast summation method. And what I'm going to really do is concentrate on the fast summation method. But so we call this approach the treecode-accelerated boundary integral PB solver. And the version 1.0 was with Weiwa in 2013. And we were using the MSMS triangulation, centroid collocation. So let me just say, the more recent version, the 2.0, we now use a nanoshaper. Instead of centroid collocation, we use a node patch scheme. We're going to illustrate that quickly over here. So if we have 5 triangles on the surface, just looking at a little patch, the centroid collocation solves at the centroids of the triangles. And we learned from Benzu Liu that it's more efficient to use something he calls node patch, which means that we solve for the for the potential and the normal derivative at the vertices of the triangle. And so these are now the discretization points. And so this is now our default method for doing the quadrature of those integrals on the surface. Preconditioning, Weiwa explained originally, we just did diagonal preconditioning. So that takes care of the variation that you have epsilon and 1 over epsilon, but the diagonal preconditioning handled that. But even more efficient is the block diagonal that Weiwa showed you. And back then we used, for fast summation of those sums, we used a Cartesian Taylor tree code. And I used this for many years until I learned something better. This is the BLTC. This stands for barycentric Lagrange dual tree traversal, and it's a fast multipole method. I'm going to tell you more detail about that. And then for parallelization, the first version was on CPU cores using MPI. But the whole point of doing this barycentric Lagrange was to make something that runs efficiently on GPUs. And so we did this using OpenACC, and I'm going to focus on that. I encourage questions along the way. It's easier than CUDA. Yeah, it's a higher level thing, and what I've been told, it's almost as good. You can do a little bit better if you program it in CUDA, but OpenACC is still very good. Mm-hmm.
And I would add that it's not limited to, if you program it on OpenACC, it should also work on other GPUs that are not NVIDIA. While if you program in CUDA, only on NVIDIA GPUs.
Yeah, there's like rapid development now. It's not even OpenACC anymore. I think it's OpenMPI, which has sort of encompassed the OpenACC. This is kind of like a year or two old. But so a prototype problem, just a Poisson equation. The potential and then the charge density. And so one way to solve this is this Coulomb integral. And so this is, of course, the essential idea in in converting the Poisson-Boltzmann equations into integral equations. And then when you discretize, you evaluate the potential at some target point xi, and you discretize the integral at some source points yj, and then the weights of these charges now will come from the charge density as well as whatever quadrature weights you've chosen. So the issue here is you can easily program this. There's a loop over I, there's a loop over j. This is a direct sum, and it can be efficiently parallelized. But the cost is still order n squared. And so the target here is to reduce the asymptotic operation count, but still preserve something that can be efficiently parallelized on GPUs. And listening to talks at this meeting, we have people who design drugs. And you have this vast library of compounds, and you search for the right one for the specific target that you're trying to achieve. And it's a similar thing here. Out of all the algorithms we have available, the target was to get something that has lower operation count than order n squared, but can run efficiently on the GPU. And so we have many algorithmic choices. And so just to tell you a little bit about, I choose to work with these tree-based fast summation methods. The DTT, this stands for dual tree traversal, was introduced in 1985. So there's a tree of target clusters. There's a tree of source clusters. And the clusters in each tree interact with each other. The tree code was developed by Barnes and Hutt in '86. It interacts between target particles and source clusters. The fast multipole method came in '87, and that's also an interaction between target clusters and source clusters, but it does it in a very specific way. And so all of these methods run faster than order n squared. The question was, which of them is going to run well on GPUs? This is an illustration of what a tree looks like with particles. A particle can interact with a cluster of particles. So a target particle can interact with a cluster of source particles. You get an n log n, that's a tree code. If you go to cluster and cluster, so clusters of target particles interacting with clusters of source particles, that's a fast multipole method. It gets down to order n. The question, though, is which will run well on GPUs? Now, these methods all rely on a separated kernel approximation. So here's our Coulomb potential with the target x and the source y. And these methods use various kinds of approximations, a series of functions of x times functions of y. And the classical fast multipole method used an analytic multipole expansion. So here's the Coulomb potential expanded in terms of spherical harmonics. And the Rx and theta x and phi x, those are the spherical coordinates of x, and the corresponding spherical coordinates of y are over here. And it has this form, and this is an important ingredient into the fast multipole method. Another alternative is the Cartesian Taylor expansion. So one can Taylor expand x around some point xc and Taylor expand with respect to y about some point yc, and you get these Taylor coefficients and you get these terms over here. Again, these are just constants now, and you have a function of x times a function of y, but you have a series of them. So I was an advocate of the Cartesian Taylor expansion. You notice that I wrote a G here, because you can do this whenever you can compute these Taylor coefficients efficiently, and for many cases that can be done efficiently with recurrence relations. The problem with these two approaches, though, is they don't really perform well on a GPU. Further along the line were kernel-independent methods. So I won't tell you the details about the kernel-independent fast multipole method by Ying, Biros, and Zorin, using equivalent densities. But I will tell you about using polynomial interpolation. Now, this idea was around the community of fast summation methods, but Fong and Darve developed something they called the black box fast multipole method. And again, it's a separated kernel approximation, and it involves polynomial interpolation, which is a wonderful way to approximate functions when it works. And so what you have over here, there are interpolation points in the target space and interpolation points in the source space. And then these are Lagrange polynomials. I'm going to spend a little bit of time telling you a little bit more about this formula. This is the approach we use, but we do it differently than what Fong and Darve did. So just to review, if you ever took a basic class in numerical methods, you probably learned about polynomial interpolation in 1D. If you're given a function f of x on an interval, and we're going to choose Chebyshev points, Sj, those have a good efficient, they cluster near the endpoints of the interval. So the Lagrange form of the interpolating polynomial is here. So you take the function evaluated. Oh, this should have been an S. This should have been an Sj over here. And then these Lk of x, these are the Lagrange interpolating polynomials, and they have this property. My pointer keeps disappearing. Okay, this is the basic definition. These are polynomials that of degree n that have this property. And the conventional form that you see in the textbooks for the Lagrange polynomials looks like this. It has good theoretical properties, but it's really poorly suited for computing. It's expensive, it's unstable. But there's an alternative form. The same functions can also be written this way. And this is, it was known to some numerical analysts, but was not well known. It was not well known, and it's kind of striking when you first look at this. It's called the barycentric. When you take this form, you get the barycentric Lagrange form of the interpolating polynomial. But it turns out that this is, I'll just quote, Jean-Paul Baroux and Nick Trefethen wrote a SIAM review article in 2004 about this method, and this is the 2-line abstract of their paper. Barycentric interpolation is a variant of Lagrange polynomial interpolation that is fast and stable. It deserves to be known as the standard method of polynomial interpolation. And I looked at the paper in 2004 and just filed it away. And it wasn't until a couple of years since now, I said, let's try to make a fast method using this. And so that, so the first thing is to say that this can be extended very straightforward way to 3D using tensor products. If you have arbitrary triple product of intervals, you have a tensor product grid of Chebyshev points. And here is, this is thinking now we're going to interpolate CR kernels, we're going to interpolate Green's functions. This is an example where we keep the target fixed, but we interpolate with respect to the source variable. And using the Lagrange form of the interpolating polynomials that you see over here, you know, I think I'm going to make a long story. I tried to make it short. I'm going to make a short story even shorter, and just tell you that the important thing is this. Let me go back to the previous page here. So if you look at these expansions for the Coulomb potential, the way that you're going to compute the spherical harmonics is with a recurrence relation. And so if you try to map that to a GPU, some of the threads will finish sooner and some will finish later. That's the problem. You get thread divergence because of the recurrence relation in computing the spherical harmonics. There's more complications involved with the FMM, but that's one of them. Even in this case over here, this wouldn't be very efficient on a GPU because the recurrence relations that we use to compute these Taylor coefficients, again, the low order Taylor coefficients, those threads will finish early, and the higher order Taylor coefficients have to sit around and wait for the recurrence relation to reach them. The good thing about the Lagrange, the Lagrange form of the interpolating polynomial, so whether it's in this form or this form, each term in this sum over here is identical just in its form. And so you can assign each thread, you can assign each term in this sum can be assigned to a thread and they'll finish at the same time. And but we don't want to use this form. We want to use this form. Now, Fang and Dov did something different. They expressed this in terms of Chebyshev polynomials. Those also require recurrence relations. And so I think this is the one to use if you want this to run efficiently on a GPU. So I'll just, again, as I said, I'm going to make this is the one I'm going to skip because it's going to take a little too long, and I'll be glad to talk about the details. But plugging in this barycentric Lagrange polynomial approximation, remember at the beginning I said that the direct sum parallelizes well. We essentially wind up with direct sums over here. And each one maps to a thread on the GPU. This was worked out with Lei Wang and Svetlana Tlupova. And then so we now had something called barycentric Lagrange tree code, well suited for GPUs. And as an example of that, with a million random particles in a cube interacting by the Coulomb potential. So there's a degree parameter for the degree of the interpolating polynomial. This is the multipole acceptance criterion that determines the interaction between a target particle and a cluster. And so that controls takes into account the size of the cluster, the distance between the target and the source. And the graph here is showing you the runtime, and then this is the error. So this is comparing the error between the fast method, the BLTC, and direct summation. So the direct summation results over here. This is the red line. Up here, this is done with 6 CPU cores. shared memory, and then 3 different values of the MAC parameter, and then different degrees, degree polynomial 1, 3, 5, 7, etc. So we can reduce the error and the runtime will increase. But when we put this onto a GPU, the direct sum gets faster, but it's still order n squared. This BLTC, barycentric Lagrange tree code, runs faster than the direct sum. This one has order operation count n log n. And so Nathan Vaughn and Leighton Wilson worked this out. And then they went further. We said, let's turn it into a fast multiple method. There's an extra ingredient that you need to get from a tree code to a fast multiple method, but it reduces it gets rid of the log n factor. And so what that means is the fast multiple method has an upward pass and a downward pass, and here that's been adapted to polynomial interpolation. We do something different than the classical Gringard-Rocklin FMM. We compute the interaction lists by dual tree traversal. That's what Apple showed in 1985. This gives us more flexibility. And then this method also has an adaptive choice between particle-particle, direct particle-particle interaction, or particle cluster or cluster-particle or cluster-cluster. So the code adaptively chooses which of those is going to be more efficient. As an example now, again with the Coulomb potential, where the parameters are set to get about 7 or 8 digit accuracy, this is the runtime now. This is the problem size. Again, this is still random particles in a cube, but the green over here is the direct summation, order n squared, as the system size increases. But the red line over here is the tree code, BL tree code. The blue dots are the it's a barycentric Lagrange dual tree traversal fast multiple method, and it's asymptotic to O of n. So we're going to use this now to solve the PB equation, and as we said, so this is a sample protein over here, and it's got these dimensions, and this is something we computed this in our earlier 2013 paper. Here we compute the surface potential and the salvation energy. The nanoshaper scale here was set to 3.5. It gave us 130,000 triangles. The runtime, so the GMRes tolerance was 10 to the minus 4. The runtime here is now 6 seconds. This is using the BLDTT fast multiple method, and this is on a V100 GPU. And we can determine that the error here is under 1%. It's 0.7%. That's determined by the scale here. Okay, 3.5 gives us that error. So this is a lot faster than what we were able to do with our previous version 1.0. And I want to show you now a computation of the Zika viral capsid. This has 1.5 million particles. It's a much larger object, but we can run the BLDTT with 3 values of the nanoshaper scale here, with increasingly fine triangulations, and then we compute the salvation energy, and then we can extrapolate. And this is an estimate of the exact value. That's how we can estimate the error in the salvation energy. And so the runtime is like this, and memory is, by comparison with other methods, the memory is still pretty modest for something of this size. And so when we attended a workshop in Brunel University in 2019, and we met Walter, and he said, why don't you, and we just had the beginnings of this, why don't you try it on the H1N1 viral capsid? And Leighton Wilson, the student, was there at the time, and so Walter transmitted it. I think you got it from Ronnie Amaro's group. So he gave us the coordinates and the partial charges, because it wasn't in the in any data bank. But but we then applied this method. That one has 14 million charged particles in bounding box. It's bigger, and Leighton managed to get it to run, and this is what it looks like. But he was only able to get it to run because it's so big with nanoshape of scale 0.5. And there were 12 million triangles. This is, I mean, just look at the difference in salvation energy. This one is also, pretty big compared if you're used to looking at proteins. But this one is like minus 31 million. We can't determine the error because we couldn't get it to run, and with a finer triangulation. But the runtime here was under 20 minutes. And memory is still modest. This is running on one of those, this is running on the same GPU. It says here, V100 GPU. Yes?
As presumably to make this even more efficient, instead of optimizing the error, you optimize the ability to extrapolate and save on the memory. Is that something that's kind of
very beautiful work. So how sensitive is your electrostatic surface on the choice of the partial charge set? Have you explored that? No.
We can determine uncertainty quantification if we vary charges, what happens? I don't know. I don't know the answer. I haven't done it.
Okay.
So you can ask that question about any.
Mike.
You can ask that question about any PB simulation, right?
Oh, it also would affect your salvation free energies.
Yes. So you want to know the answer.
Right. And then the choice of boundary box, the bounding box.
Oh, but that's just the size of the solute.
Right.
The computation has no bounding box.
Okay, that's what you meant. Okay, it's on surface. Okay, got it.
So maybe you're asking the same question. Does this give pairwise interactions between points within the, or it's mostly geared to give the salvation energy, the reaction field energies?
I didn't catch the first part.
So you have the interaction between two charge groups on the surface, or inside a charge group. So you're mostly calculating the reaction field energy, the salvation energy.
Correct.
Are you also getting the electrostatic potential at intermediate points inside the protein?
No. What you see plotted here is just the surface potential.
Right.
If you want potential at other places, we can compute that.
And you say that again?
We could compute that.
You could compute that. Is there another?
I think the next one.
It would be mine tomorrow.
So I want to make a general comment then to the three of you who have just done it. So I do like 100,000 Delphi calculations, and I'm using legacy code for that. And Antonio's using legacy code, and he's probably doing a similar order of calculation in his constant PHMD. So I think, if you guys are all doing these really interesting new things now, including you, and I really would appreciate if someone would like to collaborate with us to have something that's robust and fast and modern. And I would love to get Antonio faster and smoother and better. But even though he's perfect, I mean, I shouldn't say that Antonio's perfect, but I mean, we're really heavy users of hundreds of thousands of very similar but different calculations, moving the charges around to build up these matrices of interactions that we use for the Monte Carlo. And so it's happy to challenge each of the three of you and see if any of you would like to collaborate with us, either both,
The answer is yes.
Can I ask just something that I'm curious of? Because in my case, since I have to run PB from time to time during a simulation, quite often the consecutive frames that I have to run on, the configuration of the molecule is pretty much similar. Okay, right in front of me. Okay, so usually the conformation of the protein is very similar for successive calculations. In these methods, because I'm more familiar with the finite difference methods, in these methods, would there be a way to take advantage of that?
Yes, we see. I mean, in GM-res, that's the iterative scheme to solve the linear system. When they solve AX equals B, it by default it starts with the right-hand side B, and then it builds up a Krylov subspace. But you could start. You don't have to start. You could start with the previous X from the previous time step. And
okay.
Be further along. Yeah.
Okay.
So there's certainly opportunity.
That would be probably what.
Yeah, we haven't tried time-dependent calculations, but we'd be glad to talk to you about it.
Hi, so experimentalist here. What is this error percentage?
The error is so we computed with 3 values of the nanoshaper scale, which gave us 3 successively refined triangulations, and we computed a salvation energy for each of those, and then we extrapolate. So those points fall almost on a parabola, and so you can just extrapolate to the limit as n equals infinity. That's what this row is.
They are assuming that if the triangles are infinitely small and infinite in number, that would be the ground truth.
Okay, so it's still a comparison against a calculation.
Yes.
Okay,
yes.
So these are, as you mentioned, absolutely enormous salvation free energies. I have zero intuition about a particle like this, if that is a reasonable value, but it is in principle something that can be measured. Has it? And how close are these?
I don't think so, because this is actually the capsid of, in this case is Zika, in the other case is the swine virus. So I'm not aware of anybody calculating neither the Zika potential, but in principle it could be done.
I don't mean calculating, I mean actually measuring.
I'm not aware of anybody even measuring the zeta potential on those kind of systems.
Okay, because again, the question is, for me, is the calculation going to help me understand the physical system? And that's one way to compare it to experiment. So if you could find someone who's capable of doing that, that would be really interesting.
I don't know.
You know anyone?
No, I don't work on these. What?
Would you be able to how do you have a size limitation on the particles you are measuring your
For our method, yes, there is a size limitation because we are using NMR spectroscopy, but there are some other methods to measure surface electrostatic potential, and some of them are not really limited by the molecular size, so maybe it's applicable. But for that kind of methods, you need to introduce particular probe, and that might be practically difficult for very large system. By the way, can I ask a question? So for this one, probably you are using capsid protein without any genomic materials, right? So how do you treat the inside of the capsid?
Epsilon-1. Yeah, and there are no charged particles.
I see. But
that's right.
The shell has epsilon-1, but inside you're also putting epsilon-1, yes. Because I think the structure actually this has sort of holes. So the mesh that the nanoshaper generates is one mesh. You see it like it's close by, but it's one mesh. So the outside for you, which is the outside that is inside the capsid, would be solvent for you, right?
No.
Oh, really? Okay.
There's an epsilon-1 inside the molecular surface, and there's an epsilon-2 outside.
Right, but I think the question
charged particles are in a shell.
It's a shell, right?
Charged particles are in a shell.
Exactly. So you have within the shell. I understand that that's epsilon-1, but inside the inside.
Epsilon-1.
Okay.
There wouldn't be water there. It's
Polarizability, electronic polarizability, which is for all condensed matter, is epsilon 2.
oh, okay. Maybe it is epsilon 2. I have to look at the
this
paper
is
again.
this is the worst thing in my mind about molecular dynamics is it's epsilon 1, which is unphysical.
Epsilon subscript 1, not necessarily epsilon equals 1.
Okay, just but I think that this is I mean the tool, all these things can be easily fixed. So this is a proof of concept of the computational approach. And just to answer to Laura, so to give you an idea of the size of the system for the H1, I don't know about the Zika, but about the swine virus is 0.65 microns. So the fact that you have a huge solvation energy is actually because it's extensive.
I totally understand,
yeah.
But again, I think it's important to try to judge it against.
Of course, you're right.
Could I go back to not equations, but technique a little bit? So my question is also somewhat philosophical. So this thing seems to start improving. So the question is, what's the small size of the smaller kind of meshes where the improvement will happen comparing to just plain simple
this one
trivial no-brainer methods? Because your graphs show that at smaller meshes you don't get a lot of advantage. So you need to go into a really big system to see the advantage of this approach, right?
I think yeah, it's true that for small systems there isn't that much opportunity to make it faster.
Exactly, and like you don't need that many threads, and this meshes a bit like for the typical protein size, the advantage would not be humongous, right?
I mean, in our previous code, this would have run probably 20. This is probably 20 times faster, I would say.
But what if you compare to what Mariana said, like legacy codes, like Delphi?
Oh, well, I mean, then we have to go back to APBS. And so in our 2013 paper, we did compare with APBS, and it depends on what accuracy you want. So like if the error is above maybe 5%, the APBS would be more efficient. It would run faster. But for errors less than 5%, the tree code method, this boundary element, would run faster. Mm-hmm. Okay, but so there's a trade-off. There's some kind of, two curves of error decreasing and runtime going up, and they cross at a certain point. But all these codes are undergoing continual development, and so it's like it's a snapshot in time to say whether one runs faster than another. But one of the things to realize, so the advantage of this is for really large systems, because otherwise people have been running all of the APBS, Delphi, others. They've been running those for many years and getting satisfactory results. And it's only in cases that they want to run faster or do larger systems. These
you typically want to run faster, but I think there is certain limitation when it's like with any parallelization. If your system is not big enough, you won't get any advantage.
Yes.
Right?
Yeah.
So there is a bit of that in there.
Well, this increases at the surface, while Delphi or APBS increase with the volume.
Yeah.
So there must be some trade-off.
And scaling is fantastic. Yeah, it's really.
Can I just ask one additional question? In this kind of methods, which use the boundary, can you implement something with periodic boundary conditions?
You can do this with periodic. It wouldn't be the same kernels. You'd have to. For example, you could do Ewald summation.
Okay.
And yes, but the way you would do it is you would put most of the work on the real space. The real space is it's a short range interaction, but depending on the Ewald parameter, you can put more work on the real space calculation and then use this method to speed up the real space calculation.
Okay.
And we have a paper.
Okay, great. Okay.
Yeah. So yeah, we did that with a postdoc, a while ago. And but it didn't catch on. People are used to using PME, and it's convenient, right? But if you wanted to, you could run this with periodic boundary conditions.
Okay, thank you.
Welcome. Now, I'm going to ask a silly question. How much time do I have?
I would say 5 minutes is fine.
Okay. So I'll just again give you a quick overlook. So the question now is: so can the boundary element method be applied to the PNP equations? So this is the Poisson-Nernst-Planck equations, and so we'll focus on a formulation in a paper from Bob Eisenberg's group with two ion species. And this paper was in one space dimension, and they developed a finite difference method, and they were concerned with the time-dependent PNP equations, and they had a method for the time stepping. But we're going to use this to see these, not really the boundary element method, but the idea of using Green's functions and integral equations. Can that be applied to the PNP equations? And so the Nernst-Planck equation written over here. So the Ci is the concentration of the ith species, and then the phi here is the electric potential. And this is a drift diffusion equation. This is a diffusion coefficient, and this is the electric field that causes the particles to drift. And in the paper, they impose no flux boundary conditions on the boundary. And in that case, they also impose the total concentration for each species. And then the phi is determined by the Poisson equation here, and that couples to the charge concentrations over here, the ion concentrations. And they imposed Robin boundary conditions over here. So the eta is a parameter, and the phi plus and minus are parameters. And so these are PDEs, and people have solved them as PDEs, but we want to see if we can use integral. So the strategy here is to take the PNP equations. We're going to convert them into a fixed point problem for integral operators. So there's going to be two integral operators. Bold P here takes the concentrations and produces a potential gradient. The other operator, NP, takes the ith ion species and takes the potential gradient, and it produces the ith ion concentration in the back over here. And after this, and we're going to do the same thing. If you did a finite element method, you would do Gummel iteration. You would iterate between the two equations, but here we're going to do it. We're going to iterate between integral form of the two equations. And once it converges, you can recover the potential and the concentration gradient by a separate calculation. So again, in the interest of time, all I'm going to tell you is, you saw earlier how we solved the Poisson equation. Okay, Laplacian of phi equals rho. We convolve with the Green's function. So I can view, of course, I can view the Poisson equation here that way. And then assuming I know the charge density over here, then I can solve the Poisson equation. And in each step of the iteration, that's what we're going to do. But we can also view the Nernst-Planck equation, view that as a Poisson equation also, if you know the concentration and the potential gradient. Then it just turns, this is a second derivative. I'm looking here. It's like if you bring everything to the right-hand side, keep the second derivative on the left, it's like a Poisson equation. So just in a nutshell, that's the strategy to determine these two integral operators. And there's a couple of pages here where it's just showing you the details. I'm going to skip it. The Green's function here in 1D looks like this, and we use Green's third identity. I'm just going to go and show you some results. And for us, this is like the warm-up problem. Of course, the target is 3D, real stuff. Pardon me. But we realized we really need to see if this works first in 1D steady state. And so I'm going to, here's this page would tell you the definition of this operator. And then this page would tell you the definition of this operator. And then in the end, we have to calculate integrals like this. This is a moment of the concentration. These are Green's function integrals that need to be calculated here. And anyway, you tie it all together, and it's a version of Gummel iteration with relaxation. We get results. For example, in one case over here, with two different dielectric constants. This is from the Robin boundary condition, the eta parameter there. So the blue potential goes from a negative value on one side to a positive value. We get a sharper boundary layer when the epsilon is smaller. The ion, this is the anion concentration over here. And this is done with 100, maybe, let's see, I think the H, anyway, I think it's done with 100 points across the channel. We think of it as a channel. And we check the error. So these are uniform points. These are Chebyshev discretization points. It looks like it's second order, converging with second order accuracy. Now, this was a more interesting example from another paper, and so they did a simulation using a finite difference scheme of such a K plus channel model. There's an interior, exterior bath, and then there are 5 regions over here, and each of those domains has different. This is a fixed charge density. In 3 of those domains, it's negative charge, and take it back. Yeah, this is the total negative charge. This is the charge density here. Pardon me. And dielectric constants, mobilities, diffusion coefficients. Now, so in this, they had a conical. This is like a cross section. This is a conical bath over here. We represented it like piecewise linear. So what we're going to do is we're going to think of each of these as an interface. And in the PB equation, we're solving on an interface. And part of the job here is in the iteration, you solve for the interface variables, and then you update by doing a volume integral over the interior. And so we can apply this this approach, and I think the next one, yeah. So anyway, so how do you take into account the geometry here? Again, piecewise constant. This is what the PNP equation. A here is the cross sectional area, and so it's still a PNP type system. This is an approximation. It says variation in the radial direction is small. You know, you apply this method. This is the electric potential now across the across the model, and so it's got some interior layers, and so the charge density is this negative charge density. That's the green dashed parts over here, and the red here is the cation concentration. The blue is the anion concentration. This agrees to the eyeball. It looks similar, very, very close to what was in that paper. And so we think this is, again, a proof of concept. This is our first attempt to go beyond that PB into something that we'll see how far we can push this. We're working now, and okay, this is my team who worked on all this, former students and postdocs, and Wewa is here in the audience, and you know, just cannot do anything without helpers. And so I told you about our new version of this boundary element code. By the way, it's an option in APBS, and if you go into the documentation, and the version that's in there has recently been updated with the 2.0 stuff, but it doesn't run on a GPU because their server doesn't allow GPUs, but it will still run on a CPU. And also using these ideas and working with Tyler Luchko, we helped him accelerate the 3D RISM that's in Amber. And because we can, you know, there were lots of integrals that needed to be calculated. And so the tree code worked well over there. We'd be happy to talk to people about implementing this in other software. And then the integral equation method for the PNP equations, we're working, our preprint is up, and we're working on the 2D thing now. We'll see how far it goes. Thank you.
Thank you.